Welcome back to Virtual Precalculus. This video is only for those of you who are trying to accelerate your precal program a little bit. So in the past that had been Anjali, Sigrid, Layla, and Justin. So I hope that that group is still together and willing to do that. Anyway, what we're going to add to this week's work is section 9.3. So it's going back and working with identities, trigonometric identities some more. All right, and there's sort of a whole variety pack of identities crammed into this section. In this particular segment, I'm going to talk about double angle identities. All right. So, Justin, I know from experience that you always want this to be true. You want the sine of 60 degrees to be twice the sine of 30 degrees. I mean, I can sympathize. It makes sense. I mean, why shouldn't it be that if you double the argument, that you double the function? Okay, but if you try with your calculator in degree mode to find out what the sine of 60 degrees is and the sine of 30 degrees, you see that it just doesn't work. 0.866 is not 2 times 1/2. Okay, so as much as we want it to be true, sine of 2x is not equal to the sine of x times 2. What is it equal to? Well, here's a little proof of the identity for sine of 2x. Sine of 2x, no one will argue with me, I think, is the sine of bracket x plus x. Okay, now that we can use our addition and subtraction identities from, I think it's section 9.2 to change that and see another form for that. Right? Sine of a plus b was just sine of a cosine of b plus cosine of a sine of b. And that's exactly what we've done here, except that a and b are both just x. So the sine of 2x is sine x cos x plus cos x sine x. And we know that we can rewrite that multiplication in either order, and it doesn't matter. And so it's really sine x cos x plus sine x cos x, or 2 sine x cos x. And that is the double angle identity for sine. Sine of 2x is 2 sine x cos x. Okay, it's called they're called the double angle identities because they show us a different way to rewrite the sine, the cosine, or the tangent of 2x, the double of x. Okay, so they come in handy. You'll notice that for cosine, there are actually 3 forms of it. Okay, cosine of 2x can be written as cos squared x minus sine squared x, or we can use the Pythagorean identity to rewrite that as 1 minus 2 sine squared x, and yet again 2 cosine squared x minus 1. So all 3 of those will work. You can choose whichever one you would like, depending on what you have and what you want. Alright, so here's just a simple example of using the double angle identity for sine. Okay, we're told in example 1 in section 9.3 that we have an angle in the 3rd quadrant, which is what this means, right? That x is between pi and 3 pi over 2. And that the cosine of this angle is negative 8 over 17. And we're looking for sine of 2 times this angle. Alright, so if the angle's in the 3rd quadrant, and that's the origin, then a 3rd quadrant angle would be down here. Okay, we know that the cosine adjacent over hypotenuse is negative 8 over 17. Sorry, negative 8 signified by the fact that we're going to the left. 17, this hypotenuse is always going to be positive. And we're looking for sine of 2x. This question mark length here, okay, that's a question mark, is also going to be negative because the thing is going down into quadrant 3. Alright, so to build sine of 2x, I need to know 2, I know 2 is 2, times the sine of x, which I don't know, times the cosine of x, which I know. Okay, so the missing piece is what I've underlined in red, sine of x. And what we can do is we can use Pythagoras and say, look, a squared plus b squared is c squared. The negative doesn't really matter here because it goes away anyway. We can solve for that unknown length in our triangle, which turns out to be plus or minus 15, because the square root of 225, well, could be either plus or minus 15. But we know it's a 3rd quadrant angle, so we know to choose the negative. And the sine of x is negative 15 over 17. So that's just the piece that we needed here. In order to find the sine of 2x, which is what the question was asking us, we're going to have to multiply 2 times the sine of x times the cosine of x. Okay, so 2, and they told us the sine, well, we found the sine of x was negative 15 over 17, and the cosine of x, they told us, was negative 8 over 17. Okay, so putting it all together, we've got this, and the whole shebang works out to be negative 161 over 289, or as a decimal, 0.83. Alright, so that's how we would do that, 0.83. Alright, to find the cosine of 2x, well, we can use any of these three that we would like. I would probably choose to use this last one just because we've been given cosine of x to begin with. And the only other thing that this includes is a 2 and a 1 and some squaring. So that's just super easy. So in order to find cosine of 2x, we can use that version of the double angle identity for cosine. 2 cos x squared minus 1. Alright, so cosine of x being negative 8 over 17. 2 times negative 8 over 17 squared minus 1. So that's 2 times 64 over 289. Which is 128 over 289 minus 1. 1 being 289 over 289. And we end up with negative 161 over 289, or as a decimal, negative 0.56. Okay? So it's just plug and chug, choosing your weapons well, and putting them in the right places. Alright, just to finish this problem up, then we're asked to show that the angle 2x has to be between 5 pi over 2 and 3 pi. What the heck? Okay, so if you recall, there's a thing called coterminal angles, right? If we're right here along the positive x-axis, we haven't gone anywhere, we could call that 0, or we could call it 2 pi radians, or 4 pi, or 6 pi, or 8 pi. Every 2 pi we add to an angle, we're at a coterminal angle of that original angle. In a similar way, coming up here could be taking us to pi over 2 radians, or we could add 2 pi to that, and that would take us to 5 pi over 2 radians, right? Because 2 pi is 4 pi over 2. Coming to here could be pi, or 3 pi, or 5 pi, or 7 pi, like that. Okay, so if we say that we're between if we say that we're supposed to be between 5 pi over 2 and 3 pi, then that's the same thing as saying, let's show that this angle is in the second quadrant. Alright? So we were told at the beginning that pi was less than x was less than 3 pi over 2. If we just double all three parts of this inequality, then we get an equivalent one. 2 pi is less than 2x is less than 3 pi. And it would seem that that's where our angle should be, somewhere between 2 pi and 3 pi. In other words, somewhere between here and here. Okay, but we know this has to be a quadrant 2 angle. This angle 2x has to be a quadrant 2 angle. How do we know that? Quadrant 2 angles have what positive and what negative? X and y. Right? And x and y, well, x goes with cosine and y goes with sine. If you check it out, we found already that the sine of this angle 2x was positive and the cosine was negative. That means that the x coordinate has to be negative and the y positive. That means we must be in quadrant 2, which means our angle can't be between here and here. It can only be between here and here. So it has to be between 5 pi over 2 and 3 pi. Whew. Okay, so see you in the next segment.